Thank you. First of all, I would like to thank Ivana for the invitation and for organizing this wonderful meeting. It's been really great to hear all these talks and have great discussions. My talk will be very different than previous talks. I come from more applied side now. I used to like to do theory, but now I'm on applied side. So, oops. It's not advancing. Oh, okay, good. So we have a number of phenomena that happen in atmosphere that are caused by flows in complex terrain. For example, the top we see a broken wind turbine. That's a cause of downslope windstorm, Bora in Croatia. We have von Karman vortex tweet. If you look closely at this airplane, it's missing one engine and part of a wing. That was an incident that happened in Colorado in '92. I'll talk more about that later. We have fires that are spread by downslope winds. And then we also have just the density currents that bring pollution into the valleys. That's on one side. On the other side, we take the essence of the problem and focus on the essentials and develop theories and develop understanding. From that understanding, we have a theory that then be used to do predictions. And numerical simulations is somewhere in between. They help us sometimes understand the problem and develop a theory, but they're also essential for applications, for prediction. So I'll start with this plot that you all know of the energy spectra, sketch of energy spectra in the atmosphere. Just to remind you that the atmosphere has essentially continuous spectra. Even if there is spectral gap between mesoscale and microscale, very often it doesn't even exist. So all the scales can affect the scales in a boundary layer and turbulence scales. And that's why, especially for applications, we have to think about it. So we see gravity waves over Adriatic, again, von Karman waves breaking Kelvin-Helmholtz wave, and again, smoke being brought in the valley. That's actually Boulder by the density current. So that's one scaling. The other scaling we have for computation is scaling of Moore's law and development of CPUs. Now, the development of CPUs slowed down in recent years, and we face a problem because we don't have enough computational power to push our computations further and resolve better turbulence. To the scene came GPUs and now and other accelerators, and now we can develop codes on GPUs that can bring us a little bit further on, and we can potentially carry out even more complex simulations in a reasonable time, sometimes very complex computation faster than real time. So now to focus on problem of flows in complex terrain. I took this from Jean Cuxart's paper, where he talks about all the complexity of the flow in a complex terrain and the need for resolution. What's the resolution requirement to resolve certain processes? And he then presents this spectra again and points to the grid cell size that's needed to properly resolve certain processes, like convection, at least 50 meters, probably better, probably less than that. Valley jet, 20 meters, downslope winds, 5 meters, and so on. And that points to the fact that in complex terrain, we have input and energy at different scales. It's not just input on one scale and then cascade. It can happen depending on the physical process in question in different scales. So we have to keep that in mind. Now, going historically back, the first simulations of flows of a complex, moderately complex terrain were simulations of flow, usually two-dimensional flow, just idealized bodies. And these are papers from '74 by Frost et al. And Taylor and Gant. That was more, let's say, focused on analyzing the flow over around the body. On the other hand, we had atmospheric scientists looking at how terrain affects the atmosphere and looking at gravity waves with actually linearist model, Clamp and Lilly in '74. Only later in '77, and that may not be the first model, there may be some others that are first, but I'm aware of this one. Clark developed a fully 3D model of atmosphere. That later, much later, and I don't know how many versions later, in 2000, he used to study that incident where clear air turbulence broke airplane's wing. This is DC-8. And DC-8 was flying over Colorado. And the red color there in the plot, and this is one of the first, I guess, red colored images of simulation, represent the jet stream. And there were waves on the jet stream. And there are gravity waves due to downslope windstorm in front range that were propagating upward. And they were almost on a 90-degree angle. And that created clear air turbulence that eventually took the wing off. I don't know if you can, yeah, the wind speed of the jet stream was 55 meters per second. And there was a LiDAR in Boulder that measured vertical velocity of 10 meters per second in that same range. So, although this is not really super complex, it's an example that's still used for validation of models. Haskell and Hill, I'm sure you all heard about it. There are a number of papers that were written, validations of different models. Recently, starting, I think, from 2009, this case is used also for validation of numerical weather prediction models for larger simulations of flows of complex terrain. So Tina Chow and Bob Steve used ARPS in this case. Golas used COAMPS. We did that with WoAT. And for example, the question that comes when one tries to simulate this case and have resolved turbulence and to test LES, to validate LES, is that we need the turbulent inflow. And one way we can do that is using nesting capability, where we nest one way the fine grid into the coarse grid. Coarse grid has periodic boundary conditions. There is an inflow that's undisturbed, that goes over the hill and gets out and doesn't get back into the outer domain. So this was just one way to have idealized but realistic turbulence inflow. This approach was used to simulate the dispersion of a Syndicom butte in Idaho. And this is another old example of this dispersion study that was used for many, to validate many dispersion models. And we looked at neutral, near neutral conditions and stably stratified conditions, and we see very different dispersion pattern. Neutral conditions with stronger winds have a very narrow cross-stream dispersion, while on the stable condition, the plume disperses around the butte. In this case, it goes over the butte too. In a stable case, we are over-predicting the concentration over the butte, which means that we are really not diffusing this. This is Eulerian diffusion, not Lagrangian. So, moving on, looking at the valley flows. Dean already talked about valley flows, and this is a paper by Pinelli. Again, another test case that's from 2004 that's used often as a validation case for this type of flows. We have during the daytime as a convective environment develops, up valley flows and then down valley flows after cooling. Now, 15 years later, Babic and Becker had simulated this up and down valley flows in Owens Valley based on T-Rex field study. And here we have up valley flow and convections developing in the valley. And they studied really convective structures in the Owens Valley under these conditions, both rolls and cells. In the bottom, we have observations in black and larger simulation results in blue, light blue. And you see that it's a very good agreement. The three black dots are where the measurements were made. And then we have the other case of down valley flow. Also very good agreement. So as you can notice the pattern, we have all the simulations, more fundamental, that in black and white. Now we can do things in color. Hope that's not the only thing we're doing. Looking at density currents, I think with the first paper on density current, larger simulation on density current was by Skilnestad in 2003. And he examined all the effects, including the crossflow that enhances the turbulence in density current. And more recently, Arthur et al. In 2018 simulated the flow associated with the Matterhorn experiment that's a Granite Mountain in Utah. And hopefully this can be a little bit choppy, but there's not the nice density currents as the sun comes down, radiative cooling comes in, and density currents develop. And that points to the need for accounting for radiative, for shading effects. And now we have a shade coming as the sun sets. We cannot avoid talking about von Karman vortices, especially 100 years after von Karman organized this conference. And we see them in the wakes of islands. And that there are a couple of theories, actually, how the vortices form. One is the existence of dividing streamline and the viscosity that generates vorticity in the lee of the hill. And that was also studied numerically. Not sure that that's first time, but one of the first time that in terms of this was with shallow water equation simulation by Shar and Smith in '93. More recently, in '99, Rotuno concluded that this is not the only mechanism for creation of Lee vortices, that they can be created also because of the tilting of vorticity over the mountain and volcanicity effect. And that's how they're created. And again, they've been studied numerically, including by Nowley and et al. In different islands. And this is one of the simulations they had. Here, I'd like to point out the importance of getting good terrain data. That was one of the pitfalls that they ran into. And this is the same island, different data sets. The first island was too short at the same resolution. So one has to really check that terrain data when simulating flows over complex terrain are good. Potentially dividing streamline in this case was above that shorter mountain. We may not get what we were expecting. So moving to some simulation that we carried out, and this is when very large eddy simulation. It's 6,000 by 3,000 grid points with 100 in the vertical with 30-meter grid cell size. And this is simulation of WFIT2 field study in Columbia River Gorge. WFIT stands for Wind Forecast Improvement Project 2. That was funded by DOE. And there were a number of instruments in the area. It was a very large area. I wish there were more instruments, but it's still a very good data set. And we simulated one day of that field study, about 12 hours of simulation. What you see there sticking in the domain is Mount Hood. It sticks about 3 kilometers above the surrounding terrain. And it actually generates vortices in the wake. So they're not seen because usually they're not clouds. We can see them, but they're there. Also, there's 5 gigawatts of wind power east of Mount Hood, and those wakes affect wind power production. There are also waves, and the papers. There's a paper written by Drexler on effect of waves on wind power production in this domain. On the north of the wake, you see the gap flow speeding up through the Columbia River Gorge. So this is interesting. I don't know how this happened because I'll get out for a moment. Hopefully that's not gonna, because this is important. What is that now? I have to somehow figures all of that. I don't know what happened here. I don't know how that. Okay, I'm sorry about this. We use the data from this earlier simulation and filtered at different scales to see where horizontal shear and horizontal stress, turbulence stress divergence are becoming important. And because we want to create an argument for developing a 3D PBL parameterization. Currently, most of the numerical weather prediction models use one-dimensional turbulence parameterization of planetary boundary layer. But as we go with scales of our grid scales below 2 kilometers, the assumption of horizontal homogeneity of a grid cell that allow us to assume that one-D parameterization is okay breaks down. And this shows this. We developed 2 ratios. One is ratio of horizontal shear to vertical shear. That's the first one. The other is ratio of horizontal stress divergence to vertical components of stress divergence. And I should say this vertical components of stress divergence is just in a layer between about 40 meters and 200 meters. So that's the layer of interest for wind energy, where the wind rotors are. And we can see that as the grid cell size decreases, the importance of horizontal shear increases. At 1,500 meters, it's more than, I have them the other way around. I'm sorry, this is shear. At 1,500 meters, it's more than 5%. The situation is even more pronounced for stress divergence. So that means we really have to start accounting for these effects as our grid cell size gets small. Moving on. That's not. That's the one. Ah, thank you. So Arthur et al. Used the version of 3D PBL parameterization that we developed based on the previous work to look at the cold pool breakout in the east side of Mount Hood. That was cold pool that was observed during WFIP2 field study, and compared prediction by 3D PBL parameterization to a standard Meller-Yamada Nakanishi-Ino PBL parameterization. There were two versions, one that computed diffusion along the coordinates and the other in physical space, so horizontally. In WRF, coordinates are pressure coordinates, so they vary in time. And we see that in all cases, the fractional bias was decreased when we use the 3D PBL approximation. Also, that's in wind speed, fractional bias in wind speed. Also, the bias in TKE is significantly lower. This is distribution of bias, significantly lower with 3D PBL parameterization, in particular on a positive side. On a negative side, it's about the same for all the parameterizations. There's the reduction in bias in temperature and wind speed over, these are just sometimes used. So moving on to another field study, which was mentioned before, Perigao field study. We carried out simulation of Perigao field study one of the IOP days using both WRF and the new GPU-based model that we have developed. GPU model is a larger simulation model. First, we downscaled using 3 domains shown at the top, and then refined, and domain 4 and 5 in WRF were larger simulation domain. And domain 4 was just the fast steady domain. Here, I wanted to point to one problem that one encounters when coupling larger simulation with mesoscale simulations. Mesoscale simulations, if one doesn't use 3D PBL scheme, some of the PBL parameterizations tend to develop convective structures that are not at the right size, the numerical artifact. And that numerical artifact, when it's brought to the LAS domain, it leaves an imprint that's very difficult to get rid of. So rather than going from domain 5, from domain 4 to 5, we go from domain 3 to 5 when we carry out simulation with fast eddy. I could talk much more about this, and actually, I just have a few more words. There's a lot of data from Perigao. There were 20 scanning lidars, vertical point lidars. I think Petra is here, she can say more about it. That was the most observed field study, I think, in complex terrain for sure, ever. Here we have animation of LiDAR observation on the top and a LiDAR simulator on the bottom. LiDAR simulator based on output from fast steady GPU-based model. And if you look that time together, if you look that, obviously the flow fields are not the same. We wouldn't expect them to be the same, but they have very similar features. So we are able to capture the observed features. And that's why I put the stills on the side where I show convective early afternoon boundary layer over this double ridge in Perdigao. And you can see that they're very similar, qualitatively similar. Then we are going into evening transition and weakly stable boundary layer. Again, weaker turbulence and both in light observations and in LES. And then early nighttime, even more stable conditions. So this was more qualitative. Now, as I said, there is a lot of data and we're still doing analysis. This is just a quick way to show that we are capturing wind speeds in this case very well. Squares represent observations. They're color-coded the same way as a field from fast eddy. And you see that there is pretty good agreement. If you look at the details, there are some issues with the wind speed in the valley. There is one blue dot. In this simulations, we didn't have canopy yet, and canopy plays a role that has been already determined. We are now carrying out simulation with a canopy parameterization. Okay, there's other work on Perdigao field study. This is by Wise and Tina Chow's colleagues. And what is interesting here, that this was a flow from a west side. Well, earlier I showed you flow from the east side. On the west side, on the ridge, there is a wind turbine. This is a nighttime simulation where you see this nice wave developing over the ridge. And the dot that you see there, that's a tethered song, that's color-coded the same as the background. So you can see if the prediction is good, and it's pretty good. And the wake of the turbine is at nighttime, blue line is brought down into the valley. During convective conditions, red line in the right plot, it's actually slightly lifted. And here we have animation. Oops, sorry. Maybe I'll just skip. And this is just the convective conditions, and you can see the big difference in structures in convective and stable conditions. Moving on to another example, and this is unfortunately a sad example because this was a violent fire in Boulder last year in December, on December 30th, that burned more than 1,000 homes. It was caused, actually the cause of the fire is not completely known. It could be an underground coal mine that's continually burning and that just blew up. And there was a strong wind that spread this fire very fast. And what you see there is smoke from the fire. Okay. Yes, I'm almost there. So these are, this is the smoke. And what you can see that there is a rotor forming because of hydraulic jump. This was observed luckily by Doppler wheels, and we have radar returns. These are, and then composite, 3D composite, that's courtesy of Neil LaRue. And these are simulations of that, which we see that we are developing this downward windstorm and hydraulic jump because we are going from supercritical to subcritical fluid number, and hydraulic jump that's pretty much in the right place. So, okay, I'll skip the last two slides. They're about needs for grids, new grids, and turbulence parameterization, and I'll leave this slide up. I think that numerical simulations have facilitated development of understanding of fundamental processes in complex terrain. Development of limited area models and larger simulations contributed to that. That's accomplishment and associated turbulence parameterizations. And of course, numerical techniques. I think the community, our community, has contributed to developing numerical techniques, discretizations, and grids. I would mention the, what are major challenges? Monobook of similarity theory was already mentioned many times. Validating turbulence simulations beyond just point validations, development of methods that can better assess spatial features. And uncertainty quantification, that's also has been mentioned many times. And the only way to do uncertainty quantification with numerical models is to run many of them. And for that, we have to have very fast models. So, yeah, thank you.